Hello, everybody. Thank you so much for joining us in AI in Action seminar. I hope that everybody has enjoyed the summer and is getting ready for the start of the school year. Today, we are honored to host Dr. Srijan Das. He is an assistant professor at UNC Charlotte. He's a member of the AI for Health Center at one of the founding members of the Charlotte Machine Learning Lab at UNC Charlotte. I'm going to call it the Charm Lab. I'm not sure if it's the right pronunciation. Dr. Das can correct me if it's
No,
wrong.
this is fine. Charm Lab.
Okay. Before this, he was a postdoctoral associate at Stony Brook University. He completed his PhD in computer science at INRIA Sofia Antipolis, France. His research focuses on video representation learning, utilizing spatiotemporal attention mechanisms, multiple modalities, and both ego-exocentric viewpoints for healthcare applications. So Dr. Das has done many different types of research and has been very successful in his work and published in many very impactful journals and proceedings in areas of computer vision and pattern recognition. To name a few, they are including CVPR, NeurApes, ICCV, ECCV, and so on. He's serving the community by organizing scientific events, reviewing for several international journals and conferences. And today he is here to tell us more about his work. Thank you so much for joining us.
Thank you. Thank you.
We are
Thank
very
you for the
excited to hear
introduction.
your talk.
Okay, I'm audible, right?
Yes.
Okay. So thank you for the introduction. Um, Again, just to clarify, I'm a very much computer vision guy and less of a person working on health applications. Mostly, we design computer vision algorithms, design network architectures that can interpret images, videos, and then people come to us and say that what are their use cases, what are their problems, and we try to tailor those models for them. So my talk will be a bit technical from computer vision point of view, but the idea is to understand how, given a problem, we can tailor our vision models in your domain. So today I will be talking about two types of vision models for healthcare applications. I will be talking about generative models, of course, because that's what is going on in AI. But when it comes to clinical uses, I feel that we need models where users have more control and which users can rely on. That's why, towards trustworthy modern design, we need interpretable models. And that's why, in the second part of my talk, I will briefly talk about interpretability. So, the outline of today's talk will be that first I will be talking about my primary research area, which is uh, coming up with video understanding models that can help understanding activities of daily living performed by older adults in their homes, and how these models can be used to um, detect their cognitive decline. We are far away from connecting activities with cognitive decline because we still need to figure out good vision algorithms which can correctly identify activities of daily living, how much time they are spending in performing those activities in their daily lives, and we are working towards the technology development of that side. So today I will be talking about how multimodal LLMs can be used to detect activities, how we can tailor your LLMs for the domain that you need, where you might have limited data, you might not have um, labels or annotations that you need to train these models, how we can semi-automate the process. And since we will talk about generative approach, it is very important to also talk about interpretability of models. However, the second part of the talk will be a bit deviated from um, action recognition, because in the second part of the talk, I will be talking about digital pathology. I think most of the people in the audience will be aware of the generic workflow of digital pathology, how neural networks are used to interpret pathology images. But today I will be talking about how we can design interpretable models to interpret whole slide images, which are more interpretable, user-friendly, especially to pathologists. Um, so these are the two different topics I will be talking about. And at the end, I will try to sum up that why we need both of these approaches for especially clinical, to address the challenges in clinical problems. So firstly, I will talk about the generative approach. Before I dive into the problem, let me give an overview of what is our long-term objective. What we envision is that we have smart homes equipped with sensors, where you are even wearing ego glasses, like something like Oculus or even the Meta glasses. You have monitoring cameras and you are being monitored 24/7, which might not sound good, but at the end of the day, we want to also preserve privacy and make sure that you are being aided when you need some medical help. So we want to uh, capture all the modalities using these multiple sensors, and then all these modalities and data is going to be fed into a computer vision model, which is developed keeping geriatrician in the loop, because we need some sort of expert comments while designing these kind of models. And once we have a model, we can get a language-based word state history. I will come to that, what is it? But all this processing is going to happen inside your home. So your visual data is not going to go out of your home. What is going to go out of your home is the language-based word state history, which is nothing but basically this kind of description of what you are doing in your daily life, at what time, what activities are you performing, which objects are you interacting with, which part of the smart home you are located at a particular timestamp. All these information will be logged into your language-based one state history. And this is something which is going to be transmitted on the cloud and can be used by clinicians for personalized care, or it can be used for tracking cognitive decline. So honestly, there is a lack of this kind of longitudinal data, and we need to have this kind of technology to enable, to connect data which can be used for longitudinal studies of aging. And once we have this kind of data, we can even exploit this data for automated ADN assessments. So this is our long-term goal, but let's take a step back and try to formulate this problem, how we used to formulate this problem several years back. In computer vision, we call this an action recognition problem, which is basically video representation learning. So we want to develop a model which will take a video as input, and will classify that what the person is performing in this video. So each video will have one action. Okay, let's make it very simple. We have set of videos. Each video will have one action. Uh, the computer vision model will learn representations and learn this mapping from a video to the action labels. So this is the supervised problem statement that we have. Now, we started working on this problem, back in 2016 or 2014, we connected this data in collaboration with Toyota Motors Europe in Brussels, we have 16 elderly volunteers, um, everyone aged above 65, to stay in an apartment. We recorded them for the entire day. We provided them with a loose script that, okay, what are the kind of um, like just perform the activities that you do in your daily life. We haven't provided any strict script. Um, and we recorded them, we annotated their activities, and this is basically the data set that we play with. And we see that the activities are very natural. There are so many complex things happening. There is long-tail distribution of activities because that is how it is. It has to be, because most of the times you are walking, you are doing some actions frequently than some other actions. And there are many intrinsic machine learning problems that is inbuilt in this data set. We have two versions of this data set, and we usually try to address the challenges in this data set. When we tried to use the models that existed at that time, or even the models that comes out from the big companies, uh, we see most of these activities that we are interested in looking at are often not detected or classified correctly. And the reason is because most of the action recognition model or video understanding models are trained on internet videos. In internet videos, a cameraman makes sure that the subject is always at the center of the video, which is not the case in our scenarios where the monitoring cameras cannot make sure that the subject is always at the center of the frame. Also, um, when you are taking videos from movies or sports, the actions are very prominent. Um, the motion is also very prominent. And these kind of motions are easy to model, especially for the deep neural networks. And sometimes you can just look into the background and see what kind of activity is being performed. Whereas in activities of daily living, these videos are very monotonous, and monotonous videos are not that much available in scale in YouTube or in the internet, right? Because they won't get likes. So data is also very much limited. And this is a problem in most of the real world problems, where the kind of data that we are interested in is not available in the internet. And that's why the foundation models that comes out from many of these companies are trained on these internet scale videos and may not generalize to the scenarios that we are working on. And that's why we need some sort of domain adaptation. So specifically speaking, the challenges in activities of daily living is how to handle time. It's a long-standing problem in video understanding. Um, there are different ways to modern time, but an effective solution is yet to come, according to me. We also need to learn view invariant representations, because the same activity can be captured by several cameras which are at different orientations in your room. Um, and neural networks are not good with camera view, with rotations or viewpoint invariants. That's why we need to ensure that the model learns view agnostic representations. And finally, a lot of activities in your daily life contains actions where you have very certain motion, and it's very difficult for these models to pick up these certainties in the videos. That's why we need to build models which can learn or recognize fine-grained motion or information in the videos. So these are the challenges that we need to address, and that's why people came up with different models. um, First question is how to handle time. Back in 2017 or 2018, when I was doing my PhD, we were very much using 3D convnets, and that's when 2D CNNs were extended into spatiotemporal kernels. So you have a cuboid which converts across the entire um, volume, or the video or the space-time volume. These models have been very successful and have been used for several years. But in 2020, with the emergence of vision transformers, people kind of shifted towards using transformers because the throughput is good, their effectiveness is pretty good. When you have large scale data, it's better to use these kind of vision transformers. So vision transformers with spatial and temporal attention is something that people started using. And now in 2025, people use foundation models. So there are models like KNIP, where you have a vision encoder and a language encoder, and there has been attempt to bridge the gap between vision and language encoders, and these kind of dual encoder architectures are used nowadays for understanding videos. So these are the three different kind of designs that people are using from time to time, depending on the problem and the scale of data they have. And on the other side, in order to specifically address the challenges of activities of daily living, a lot of researchers also use 3D poses or key points of humans performing actions. Um, this was a bit difficult 10 years back when we had to make sure that your smart home is equipped with depth sensors, because on the left hand side you can see the poses captured by a Kinect sensor. But nowadays, you basically don't need depth sensors to get these kind of skeletons or 3D key points, because this image and even this video at the right are 3D poses extracted from only video. We don't need sensors anymore because we have very good deep learning models which can just take your RGB video and can generate this kind of high quality 3D human poses of person performing activities. But why do we need this kind of 3D poses? Because since they are 3D, they are robust to illumination changes, viewpoint invariant, and they provide geometric information about the actions being performed. Um, Now, this is a big problem in computer vision, is that we expect the models to perform the way humans perceive the environment, but it is a bit unfair because to the computers we provide images, they don't have 3D information, but we as human perceive the 3D info, we have access to the 3D information of the world. So it is always good to come up with vision algorithms which can bridge the gap between 2D and 3D vision. And towards that attempt, we have been always trying to use 3D poses, because this is an attempt to bridge the gap between 3D vision and the 2D images or videos that we provide to the models. And if we are able to do that, you will be able to design models that can localize their attention towards the human parts which are contributing to perform an action. And this is the kind of heat map that you get. So you can basically understand that, okay, if the action is happening somewhere here, um, the movement in the 3D poses when translated into some sort of attention, and when enforce the modern to focus on those areas. So we have been working a lot on approaches combining RGB and 3D poses. We did that in 3D CNNs. Um, then with vision transformers, we did the same with video transformers. And now with foundation models, we also introduced poses into this kind of foundation models using where RGB and language are already aligned. Uh, these combination of RGB and 3D poses are not straightforward fusion of two different modalities. There are specific ways of doing that, and we have explored those different research directions. And we prefer to use something like knowledge destination, where you need the 3D poses only at training time, but not at test time, because getting these 3D poses is easy, but you need some time to extract those poses, right? Even if you are using some sort of deep neural network, or you need some sort of depth sensors. We don't want to do that. That's why most of our methods of combining RGB and poses have a specialized way of doing that, either through knowledge destination or through some machine learning strategies where we don't need these 3D poses at test time, making these kind of algorithms more robust and flexible to real world scenarios. So this is something that we have been working for several years now. Um, but in 2024, with multimodal NLMs, with ChatGPT everywhere, we were kind of like, okay, now it's time that we have to take a step ahead. We have to integrate these kind of modalities into NLMs. This is what we wanted to do. There were already some existing NLMs that integrated videos into NLM embedding space, and we thought of using that and check whether activities of daily living are getting recognized or not. One good thing about these models are that we can go beyond just learning a set of action labels, but now we can ask questions, we can chat with the chatbot, and you can basically ask any questions regarding the video that you input to the model, which is a good thing. But when we tested a video in which is captured inside house, where even the subject is centered in the frame, we get to see the modern is doing good in understanding the different objects present in the scene, but the temporal understanding of the modern was not good. I can show some more example. So here is a person. This person is taking medicine near a cupboard, and what we see is the action this modern recognizes is that the man is seen opening a closet door, pulling out a book, reading it, and then putting the book back in the closet. And it's a classical example of the modern hallucinating, where you get to see that if the person is near a bookshelf, it is more likely that the person is using or interacting with a book. And that's when we realized that these models are very much biased to what it has seen in its training distribution. Even if we say that these models are very generalized, when we use it for our domain, we get to see that most of the certain scenarios, or most of the critical scenarios we are interested in, they are not getting recognized by these foundation models. And that's when we decided that we need to um, adapt these models for our scenarios. And that's when we came up with our foundation models for activities of daily living, which is published few months back in CVPR 2025. We call this model Navidan. What is Navidan? Navidan is where we integrate videos into NLM, but this model is fabricated for understanding activities of daily living. Why is this important for this talk? Because we have fabricated it for activities of daily living because we were interested in this problem. If you're interested in some other problem, you can do it for your problem statement, right? And the experience in building this model is kind of very interesting because there were different challenges. First of all, we have very we don't have like lots of videos. We have very limited number of videos, so we need to fine tune these models. But in order to fine tune these models, we need videos and question answer pairs. That's what we call visual instruction pairs. If you want to train LLMs or multimodal LLMs, you need user queries and its associated answers. In most of our problems, we don't have that kind of data. So that's challenge one. Challenge two is that, do we train multimodal LLMs with the design that we already have, or do we need to also do some sort of adaptation? And basically, when we started working on this, we thought of, like, we have seen in the past that skeletons or 3D poses are helpful. Um, we also see that most of the activities of daily living involve objects. Can we involve a modality which includes human object interaction as a cue? So we wanted to add several other modalities into the LLM embedding space. For that, we need to also tweak the design of the existing multimodal LLMs. And after you do that, when you train a model, you also need to benchmark these models, right? And for that, you need some sort of tasks and you need some benchmarking protocols. So we had to do all these things from scratch. What we have is a model which is trained on large video instruction pairs but doesn't work on our data. So that's why we tried to address each of these scenarios where we came up with our data set. That doesn't mean that the data set is created by annotating using human in the loop. We came up with some sort of semi-automated framework which can automatically generate visual instruction pairs to train these kind of multimodal LLMs. We also designed our model where we integrated different modalities into a common unified embedding space, and we also came up with with many benchmarking tasks. So um, the first thing that I will talk about is ADN-X, which is the data set that we came up with. So the only thing that we had is some public data sets where we only have the videos and its associated action labels. We didn't had any visual question answer pairs. And I know that there are some data sets for even your problem where you will have visual question answer pairs. But this is not true for many practical scenarios. That's why we wanted to build this data curation framework. So what we do is we first generate long videos because we wanted to process very long videos. Um, because most of the data sets that exist in the state of the art are trimmed videos which spans 3 to 4 seconds. So we take these trimmed clips, video clips, and we try to concatenate them in such a way that we get a very long video. But how do you get a long video? First of all, we ask LLM that, okay, what are the activities we should concatenate so that it resembles a practical scenario that what a person can do. For example, a person is drinking water and then a person is eating snack and then a person is doing phone call. So the sequence of the activities to be performed is given by LLM. Once we have that, we take these video clips, we do a person detection, and we crop out only the person of interest, because we have to generate some sort of annotations for which we need LLMs or VNMs in the loop. And VNMs are very much prone to introducing information from the background, which is not of our interest. So if you have some sort of way of cropping the region of interest, we recommend you to do that before feeding it to your VNMs. Because if you just input the important region from the videos or the images that you are using, VNM will just look into them, because VNMs are, even if you are using very good prompt engineering, VNMs are not good in catching up the important region in the images. So we do something called person augmented generation, where we just crop out the person of interest where the action is happening. And that can be done basically by using some sort of detector. And once we have these small clips of videos for each action, we kind of concatenate them. And for concatenating them, we basically just do a temporal stitching. For each frame, we get image captions using an image captioner. And if there is a video with 20 frames, there will be 20 different image captions. We take all these captions, concatenate them, send it to GPT, and ask GPT to summarize the video. And while doing this, we also provide the action sequences, because that is the only ground truth that we had. And that's what we say is that it is a weak supervision of action labels. Because when we provide this weak supervision, it is just a way how we use some sort of ground truth data available to us, because it helps us to generate very good video descriptions. If you have a good video description, it will help you in generating a good question answer pair. How do we do the question answer pair generation? So once we have a good video description from GPT, we take this description and send it back to GPT and ask that, okay, now this is a description of the video, generate 5 question answer pairs. And these question answer pairs should have the properties that we need. For example, ask one question about the activities, one question about the objects present in the scenarios, and you can basically categorize the different kind of questions NNM should come up with. So now you have the videos and you have 4 to 5 questions per videos. So now you have the data which can be used to train your model. Once you have the model, once you have the data, now we can go ahead to train the model. And this is a very naive model. You have video, you have text, right? And you integrate everything into the VNM or large language vision model, which consists of some MNPs and the NNM. If you do that, it does not have a very good ADN understanding. So what we do is we integrate other modalities, because we used to do that in the past and we wanted to do this even in the NNM embedding space. So we added additional modalities like human object interaction cues and 3D poses. We take the features for each of these modalities and we try to project them into a common embedding space of the language model. Now, when we try to do this, it comes with an additional challenge, and that's a machine learning challenge, because now we have a lots of modalities and we are trying to project everything into the same embedding space, and there will be conflicting gradients. The conflicting gradients will hamper the optimization process. And then the question is how to combine all the modalities together. And that's when we came up with a multimodal progressive training. It's a very easy, simple method to train your LLMs if you have lots of modalities you want to embed into your LLM. How do we do that? What we do is we start solving easier tasks first. And then we go on integrating the modalities in a sequence, ensuring that the difficult modality comes at the end. So we increase the complexity of the task one by one. And that is what we call curriculum learning. So there are different stages of training the model. In stage 1, we train each modality by feeding them into the LLM embedding space. In stage 2, we take 2 modalities which were performing better in stage 1. How do you track that? By tracking the losses. If your loss is going down, that means it's a modality which is optimizing very well compared to the others. We take the best 2 modalities, we integrate them in stage 2. The projections, the MNPs that we use, they are being initialized from stage 1. Now we take the third modality, which is the remaining modality, and integrate them in stage 3. Um, and the projector is initialized again from stage 1, but for skeletons and for videos, the projector is initialized from the previous stage. The good thing here is that if you have n modalities, you go on doing this in n stages. And in each stage, you go on integrating a modality. So it can be generalized to n number of modalities. And it is a good way of combining so many modalities together by increasing the complexity of the task slowly. Now we have a model, and this model is called Navidan, where all the modalities are integrated into the embedding space. Remember, when we test this model, we don't use the object modality or the skeleton modality, because all these are transformers. You can get rid of any of these modalities at any time. You don't need to take care of, or you don't need to do any sort of padding or anything. This is just a way of training the model where we use the breadth of the data, because we don't have enough data. We only have 100,000 video question answer pairs, whereas some of the models are trained on millions or billions of data. And that's why we use different modalities. But we cannot expect these modalities to be present even at test time. So for benchmarking, we used different other data sets: Charade, Smart Home, NEMA, Toyota Smart Home. The reason I'm pointing out these data set is because none of these data sets have been used at training. The training distribution is completely different and comes from a different public data set. The tasks that we are doing is we do some MCQ task, and we also do video descriptions. And here are some descriptions from Navidan, where we get to see that it basically does not make mistakes compared to the other state-of-the-art methods. When we compare our models with the state-of-the-art, Navidan outperforms other models like Video Nama, where you have like 2.6 million question answer pairs, or even like models using GPT, where you have 1.5 billion images being trained, compared to our model where we are just using 100K question answer pairs. But this is a model that we developed 1 year back, where the NLM that we are using is Vicuna. I can tell you that the in-house model that we have now has much higher accuracy than what you see here, because now we are using a more powerful NLM. The good thing about this kind of framework is that you can anytime switch your NLM, you can anytime integrate any modalities, and basically you can also augment with other modalities if they are present at inference. So these models are very flexible and robust, and they are domain adaptive. So if you get a foundation model which does not work in your scenarios, but still they are generalizable, you can take some unlabeled data, you can design your semi-automated pipeline for generating visual instruction pairs, and you can train your model and make it domain adaptive. This is a demo that we have in UNC Charlotte. So basically, you have a portal, you can just input your video, and there is a user, and the user can ask any question about the video, and you can go on conversing with this chat agent. And it basically answers most of the questions correctly, even if you have multiple person in the scenario. Okay. Yeah, just wanted to point out that even in this video, which the existing models were not working on, here you can basically see that our model has kind of addressed all those hallucinated, that kind of wiped out all those hallucinated statements, and it can perform pretty well on this kind of videos. And this work is done by my PhD students, Dominic, Orko, and Manish. So if you have any specific questions, of course, I am here to answer them, and they will be also happy to answer. And we have our code bases and everything public. So I will take the questions at the end. I have like around 5 or 10 minutes to wrap up the second part of the talk. This is all about the generative approach, and I will quickly move to the interpretable approach. And I promise that it's not going to be a detailed discussion, but it is going to give a perspective of how we can use or we can design interpretable models. And I also assume that like most of the people in the audience, they are aware of how digital pathology works, what is the workflow. So I will not go into the details of the workflow for this. So yeah, the use case here is digital pathology, and the AI tool that we will be focusing on is multiple instance learning models. So before going into the details, let me first talk about a very generic workflow. Um, in computational pathology, unlike natural images, we have whole slide images. They are gigantic images with gigapixels, and you cannot take the entire image and send it to a neural network. So what we do is we decompose them into non-overlapping patches. So each WSI is decomposed into n patches. And for each patch, you send it to a feature extractor, and for each patch, we get a feature. And this feature extractor can be some sort of deep neural network. Once we have these features per patch, we aggregate these patches in a multiple instance learning framework. This is a shallow deep learning network, which kind of aggregates all the patches. So it mostly contains a patch attention module, which kind of gives importance to each patch in the whole slide image. This kind of data comes with only one global slide level annotations, mostly because annotation is so costly uh, for pathology data. But what we expect these models to do is to not only solve the slide level tasks, but also to localize where the cancerous cells are present. That means we want to do some sort of weak supervision where we only have global labels, but we expect the models to not only provide us the classification labels, but also detect where is the what is the region of interest. So that is what is done by multiple instance learning, where you take all the patches for a whole slide image, you get the scores for each patch, and then we do a weighted summation of the patches. And then this weighted summation is classified into the slide levels that we are interested in. So this is how generic computational pathology workflow works. Uh, so there are basically two stages. Once the first stage is patch level feature extraction, and the second stage is slide level aggregation. We have made lots of contributions in both of these stages. Today, I will be talking about only one of the work in stage 2, which is SIMIN, which is taming deep MINs for self-interpretability in gigapixel histopathology. So let me briefly talk about stage 1, what happens in stage 1. So once the WSI is provided, we decompose them into patches. We send it to a deep neural network, and for each patch, we get some features. But what is this feature extractor? This is a deep neural network. But this deep neural network, how can we train it? So we have to take a pre-trained model because we don't have any labels to train this model, because you have only a global label. You don't have label per patch. That's why training this feature extractor is difficult. One naive solution is that you can take an ImageNet pre-trained model, but then the domain gap is very high. That's what. That's why what we need to do is we need to use something called self-supervised learning, where we can take unannotated pathology data and we can basically train the visual extractor or the feature extractor with this data even without using any annotations. For example, take the data, rotate it, or do some sort of zigzag puzzle and ask the model to predict those augmentations. So the model becomes agnostic to the perturbations. The most common one in pathology is using this kind of contrastive losses, like SimCLR, where you take your data, you generate two different views of the same data, send it to each branch, and then ask these representations to attract each other because they come from the same data. And you ask these representations to repin with all the other images in the same batch because all these images are different images from this image. This is called contrastive learning. And another famous self-supervised learning framework is mask autoencoders, where we basically provide a part of the image to the network and ask the network to predict the other part of the image. This kind of methods can be used to self-supervise your feature extractor where you don't need any annotations. But the problem is that it works very well with natural images, where the important region is localized in a very small area. Therefore, the activations or the attention is only localized into a very small region when we use this kind of self-supervised learning methods. But in pathology, the important regions can be spread all over depending on what kind of cells are present. And that's why we need to dispersify the attention. And that's why we came up with a self-supervised learning method that can dispersify the attention within transformers. I'm not going into the details of the method, but this is a quantitative result. This is a pathology annotated data of which regions are important. This is the baseline where you can see how sparse is the attention. And this is our model where you can basically see the overlap of the important regions with the pathology annotated data is quite high. But going into the Schneid-Levin aggregation, this is a work that is published in last year's CVPR. I will quickly go through this method. MINs are very shallow deep neural networks where you take the features per patch and try to aggregate them for a Schneid-Levin task. These networks are very good with performance, but they are not interpretable. But if you go 20 years back, we used to use handcrafted pathology features. And these features, they are not as effective as deep features, but they are interpretable. Is there a way how we can connect them? Can we jointly leverage the best of both worlds, where you achieve interpretability and you also get very high performance? And that's when we came up with SIMIN. Take your WSI, decompose them into patches. For each patch, get the nuclei maps. It's very easy to get. You can use something like HoverNet, which is pre-trained on PanNuke dataset, and you can get these kind of nuclei maps. From these nuclei maps, you can get handcrafted features. These handcrafted features can be morphometric properties, or it can be spatial distribution properties. And at the same time, also get the deep features for your patches. Once you have the handcrafted features and the deep features, send the deep features to your conventional MIN to perform the Schneid-Neben task. These conventional MINs are very good at doing attention of the patches. So it is very good at identifying that which patches are important. But it cannot tell us which features are important to perform this Schneid-Neben task. That is what SIMIN is going to do. How? Take this information that which patches, which top K patches are important. For those top K patches, take the handcrafted features and send it to the self-interpretable branch. In the self-interpretable branch, where we take only the top K patches important for performing the Schneid-Neben task, we take the features and we provide a feature-Neben attention. Remember that these are handcrafted features, so we know what features correspond to what properties. And then we don't use any nonlinear activations in self-interpretable branch. So basically, when we come up with the Schneid-Nebens, the Schneid-Neben can be derived by a linear combination of the input to the self-interpretable branch. So for a particular output of this model, you can basically derive that which features are important, since it is just a linear combination and we haven't used any non-linearity. So we preserve the interpretability of the model. Once this is done, we can see that our model can outperform or is very competitive with the existing deep features. We tested it on 3 TCGA datasets for 3 different Schneid-Neben tasks. Our model is able to provide this kind of automated patch and feature importance report. However, the limitation of this method is that when diagnosing a cancer patient, WSI, a pathologist not only annotates the salient regions, but also explains the diagnosis by identifying key visually discriminative pathology concepts, such as glandular or nepidic growth patterns in lung adenocarcinoma or cretinization patterns in lung squamous cell carcinoma. But our models, SIMIN, operates on handcrafted features, and it's very difficult to define these concepts. But now with language models and good text embeddings, it is possible to generate these kind of visual concepts which can be defined or which can be described in language. And that is what we did in our next work, JECO, which will be presented in October in ICCV 2025. And all these work related with digital pathology is done in collaboration with Stony Brook Medicine with Sarthak and his advisor Pratik Prasanna. So to sum up today's talk, I discussed what is going on with computer vision, how you can take a foundation model and adapt it to your domain. And there are different ways to do this. First, you should have your semi-automated pipeline to generate visual instructions. And you should also have a very good training strategies to train your foundation models. And at the end of the day, if we want these models to be deployed in clinical settings, we want to have some trustworthy models to deploy them. And that's why we need interpretability of these models. I have shown interpretability in digital pathology where you don't need to compromise accuracy, but it can be also done within generative models, and we are working towards that direction. So that's all from my side. Thank you.
Thank you. Thank you very much for really interesting presentation. We really appreciate you. Okay, so do we have any questions from audience? We have one from Dr. Devane. Would you like to ask your question?
So do you use your fine tune? Okay. Yeah. So do you use your own fine tuned local LLMs? Yes. So the NNMs that we use, the work that I presented, it's a Vicuna. It's the NNM is trained on some data set, but we have fine-tuned it. There are two different ways. When we integrate videos, we have tested that if you don't have enough data, it is better not to fine-tune the NNM, but to only train the projectors, only some MNPs which will align the image pixels or the video pixels with the NNM embedding space. However, if you are doing a task where the language that you are expecting out of the NNM is very different from the generic language that comes out of NNMs, then it is recommended to perform the fine tuning of NNMs. For example, we also work on vision language action models. That means the NNMs will be able to provide robotic actions. Now, NNMs are not trained for doing this task. That's why for this kind of task, we have to also fine tune the NNM. But for action recognition, for video understanding, we don't prefer to train the NNMs, and we have seen empirically it doesn't help. Whereas I know if you have enough data, or if you have some sort of problem statement where you think the NNMs are not aware of the terminologies, that's when I think it is good to fine tune the NNMs.
Very good. Thank you. Thank you so much for your response. We have time for maybe one more question. Okay. Very good. Thank you so much. It was a very interesting talk. At the beginning, I was thinking, okay, ADL, but then I remember that we have elderly relatives that we use. We actually use cameras to kind of just make sure that they are fine. So it seems like to be a really interesting technology that could help a lot of people, especially those and actually their families who are a caregiver for patients with Alzheimer and dementia. So that was a really interesting talk. We really, really appreciate your time. And we have one question.
Okay.
Okay. I'm assuming it's digital path. What digital pathology data did you train your models on? Do you use publicly accessible data set, or is there a need for digital pathology data lakes?
Okay, so the data sets that we have used, TCG and NUNGs for NUAD versus NUAC classification. We have used TCGA BRCA for IDC versus IHC classification, and then we have used TCGA CRC. So we have used all the public data sets to train these models.
Very good. Thank you so much. Thank you for your time, and thank you for a wonderful presentation.
Thank you. No problem.